So, hi everyone. Welcome to the 10th talk of the seminar. And I think, as Anastasios pointed out, this is one of the very unique talk from many perspectives. One, we are sort of like branching out in the seminar a bit more to topics that are related, but like loosely related to security and privacy. And second, this is also like one of the talks where it's more geared towards like gentle introduction, and also like it's like a good overview, I believe, of and like a lot to learn for everyone. Our guest speaker, as you know, is Anastasios Angelopoulos from UC Berkeley. He is a fourth-year PhD student at Berkeley, advised by Michael Jordan and Jitendra Malik. And yeah, we are glad to have you here today. And yeah, the virtual stage is all yours.
Thanks so much, and thanks for the invitation.
Mhm.
Okay, I'm going to share my screen now.
All right.
You see my iPad?
Yeah.
Good. Okay, let me also move the screen so that I can see you guys. Okay. Hi, everyone. Yeah, thanks so much for having me. It's an honor to be here. The talk that I'm going to be giving you today is, I titled it in the message to you guys, A Gentle Introduction to Conformal Prediction and Conformal Risk Control. And the thing that unites these ideas is that they're all forms of what has started to be called distribution-free uncertainty quantification. And the purpose of distribution-free uncertainty quantification, at least as I'll present it here, is basically to take any like machine learning model that you have and somehow endow it with some statistical property like a prediction interval, which is kind of like a confidence interval, except the thing inside the interval is like the new observation. So the setting is like I have a neural net and it takes X's and turns them into Y's, but you don't know how good it is. And so I'm going to give you an interval around Y hat that's supposed to contain the new Y. And it's going to do that with high probability. Okay, just like a confidence interval contains the true underlying parameter, high probability. And the nice thing about the methods that I'll present is that they'll work for any pre-trained model. They'll be assumption light, maybe actually not assumption free, but assumption light, in the sense that they don't assume anything about the distribution of the data or the form of the model. They work in finite samples, so they're not asymptotic results. They work for any n. And they're really easy to run. So, this is not even as complicated as Bootstrap. This is something that you can run, that takes less than a second on your laptop. So that's what we're going to learn how to do. In particular, the two techniques that I'm going to present, one of them is called conformal prediction. So you guys might have heard of conformal prediction before, but if you haven't, don't worry, because we're going to go through and understand the algorithm in very close detail. It is not a difficult algorithm to understand. The motivation behind this is basically like, let's say I'm a doctor, and I get an MRI of somebody's brain, along with a classifier that predicts what diagnosis somebody has. So either they're normal or they have a stroke in this case, right? Let's say that the classifier just gives you a point prediction. So let's say the classifier just says somebody's normal. The question is, as a doctor, do you take that into account? Or like, how do you proceed with that information? And the answer is basically because even if the classifier is like 70%, 80% accurate, you don't know that the patient doesn't fall into that 20%. So you really can't actually take the model's output as much information. Instead, what conformal prediction would give you is a set of diagnoses, like normal, stroke, and such that the probability this class contains the ground truth is greater than or equal to 90%. Okay. And the idea there is then the doctor might be able to use this set to go do differential diagnostics afterwards. So they might say, well, let's do further testing just to rule out a stroke because the model can't rule it out at 90%. Right? And then in conformal risk control, the story's a bit more flexible. So in conformal risk control, what you can do is you don't have to just have prediction sets with coverage, right? So this property is called coverage. With conformal risk control, you can certify things about your model, like if I'm trying to do tumor segmentation, that these segmented outputs are going to contain 90% of the ground truth tumor. So the expected fraction of tumor that I missed is less than or equal to 10%. All right, so these are sort of like, remember that we didn't have any guarantees about the model before we did this, right? So we put it through an arbitrary disease classifier and an arbitrary segmentation algorithm, and then we got these guarantees out. And so that's basically the motivation of these ideas. Does anyone have any questions before we move on, just about like the high level idea?
No, not really. I guess you can move.
Oh yeah, sounds good. Yeah, I'm gonna ask you guys for I'm gonna stop for questions at several points. So feel free to, raise your hand even if you want. Like, how do you do this? Can you do this in here?
Yeah, I think folks can do.
Okay, we do have a question. How is it different from just top K label predictions? That's a great question. So it's different from top K. And let me lower my hand. There we go. It's different from top K because the size of this set is adaptive depending on the difficulty of this image. So it's like top K, where K is a function of X. And the benefit there is you'll get big sets when you're uncertain and small sets when you're certain. Does that answer your question? Great.
Is it fair to say it's like dynamic top K with guarantees?
Yeah.
Or,
In classification, I would say yeah.
I see.
Okay. So let's just get a little bit more formal here, set up some notation so we can talk about the problem. In the image classification setup, we're given X's, which are images, and Y's, which are class labels in 1 through K. All right. So if this is ImageNet, K would be 1,000, and these would be, like airplane, cat, dog, beagle, blah, blah, blah. All right. And now the other things that we're given 2 things. We're given a calibration data set, okay? So the calibration data set has N IID. Actually, they don't even need to be IID. They can be exchangeable data points coming from some distribution. So you can think about N as being something like roughly 100. And these are pairs of images and labels, right? So you have N calibration data points. They're fresh that the model hasn't seen before. And then we also have a model, pi hat sub y of x, which estimates the conditional distribution of the y's given the x's. All right, so it gives us an estimated probability distribution over the labels given the image. And now our goal is to predict some set, which I'll call C of x, which is a subset of the label space such that the true label is in this set with high probability. All right, and that's called coverage. All right, so this is going to be our main goal with conformal prediction. Okay, so you should notice here that we want this to be close to an equals sign, by the way. So the user pre-specifies alpha, and then I'm going to give you a set C, which is a function of the calibration data set, and I want to kind of hit 1 minus alpha. Right? I want to give you a set that has the right confidence. Okay. So what do these sets look like in practice? What I did here is I took 3 squirrels from ImageNet, and I plotted them along with their prediction sets from conformal prediction. Okay. So on the left-hand side, there's an easy squirrel. Okay. So why is the squirrel easy? Because it's on a fence, the squirrel's in full view, the background sort of makes sense. The model has seen a lot of squirrels like this, so the set will be small. But then if you go all the way to the other side, here's hard squirrel head cut off. Hard squirrel's background is gravel, no suggestion that it's a squirrel. Its tail kind of looks flat. It actually, in some ways, does look like a marmot, which is what the model thinks it is. But in any case, the label is a squirrel. But in this case, the model is uncertain, right? Because of all these factors. And so it outputs a big set. Right? So the sets are bigger when the model's uncertain because there's some property of the image that's difficult. Okay. And as you can see, the top one was wrong, but the second answer was correct. All right. So a bit more precisely, what do we want from these sets? We want them to have correct coverage, right? So that's why we are doing this whole thing. We're actually going to guarantee you this. Right? That's definitely the main goal. If we don't have that, we have nothing. But that's not enough, okay? Because there's trivial ways to get correct coverage. So one trivial way to get correct, actually, can anyone guess what's one trivial way to get correct coverage?
You can give top 5, I guess.
You can give what?
Top 5 predictions.
So top 5 won't necessarily give you correct coverage, right? So if I set alpha to be equal to 0.001, even top 5 won't give you 99.999% correct answers. But one trivial way to give you correct coverage is to just take C of X to be equal to the label space. Right? So I just give you all classes always. I say it could be anything. Right?
Yeah.
So that's not enough, obviously. But that's just to show you that coverage is kind of a weak property. Right? So coverage itself is not enough to give you meaningful sets. We also want more from them. By the way, there's a trivial way to get exact coverage as well, which is to take the whole label space with probability 1 minus alpha and to take the null set with probability alpha. Okay. But the problem is that these sets are huge, right? They contain, let's say, 1,000 labels. So that's not good. Oftentimes for decision makers, we also want the sets to be small, just so that they can be interpreted by like a human reader. And maybe most importantly, we want the sets to be adaptive to the difficulty of the example. So if you guys know what conditional coverage is one target that people often choose for these prediction sets. But just the main idea should be that you should have behavior like this, that for hard squirrel, the sets are big, and for easy squirrel, the sets are small. All right. So conformal prediction is an algorithm for helping you achieve this. Okay. And the idea of conformal prediction is, what if we learn a rule to predict the sets using our calibration data set? And we're not going to learn the rule using gradient descent or anything complicated like that. It's just going to be like a really simple statistical procedure. You basically calculate a quantile, and you use that quantile as a threshold for your probabilities. Okay, just in the classification setting. The algorithm's simple enough that we can just understand it exactly in the next like 3 to 5 minutes. So we're just going to dive into it. Okay. So step 1 of the algorithm. Step 1 of the algorithm is get the model softmax score of the correct class. Okay. So what do I mean by that? What I've drawn below, I'll explain, is I made a neural net. Then I took X sub I, my ith calibration image. What are we saying? Prior knowledge of the label. Yeah, so let's talk about that maybe after we go through the algorithm. Okay, so what have I drawn here? I took the neural net, I plugged in X sub I, our ith image, and then out I got the following plot. Okay, I got for each class, class 1, class 2, class 3, this could be airplane, cat, dog, blah, blah, blah. I got the model's estimated probability, right? I got my pi hat y. And now what I do is I look at y sub I, the true label of X sub I, and I take this level here and I call it E sub I, which is that thing. Okay, so I look at the score of my true class. If your model's good, this thing will be large, right? But your model's not necessarily good. All right. Does that make sense? Good. Okay. Now I have n of these calibration data points. So I'm just going to call this a sequence here. So I do this for each of my calibration data points. Now I have a sequence of model softmax scores. All right. Now, step 2 is I take the sequence of model softmax scores and I take roughly the 10% quantile. Okay. So it's not actually the 10% quantile. It's just very slightly smaller. And I'll show you what the correction is in a second. But just conceptually, I've written it here in like NumPy notation. But I'll just draw a picture. What we did is we took these E sub i's, which are the model's top softmax scores, and then we made a histogram of them. Right. And then we looked at this level, Q hat. Q hat is the level such that 10% of things fall below and 90% of things fall above. So how should we interpret Q hat? Q hat is the level such that at least 90% of our calibration examples have a softmax score above Q hat. So if n goes to infinity, Q hat is actually the true 10% quantile. And then if you give me a new label, the probability its softmax score lands above this threshold is 90%. Exactly. Now, when n is finite, you have to do this little correction, which I'll show you in a second. But that's the interpretation of this quantile. It's some threshold such that the probability you fall above is 90%. Okay? And now step 3 is you form prediction sets. Okay, so basically we've finished the statistics part, and now we can just deploy. And the way we deploy is we take all classes whose score exceeds Q hat when X test is input. So I give you a new test image, and then I do the following. I'm going to take X test. I'm going to plug it into the neural net. I'm going to get the softmax scores. And then I'm going to threshold them at Q hat. So that's the level I got from step 2. And then these 3 guys, so that's 1, 2, 3, 4, 5, 6. So these guys will go into a prediction set, which I guess I've shown in green. It'll be 2, 4, 6. Okay, so that's conformal prediction. We just finished. X test, that should be. Okay, so when you run this procedure, you get a guarantee. Okay, the guarantee that you get is this. It's down here. And this is kind of like the magic of conformal. The guarantee that you get is that you have coverage. Okay, so not only is the label contained in the set with probability 1 minus alpha, but also the set's not too conservative. Okay, so the set, let's say I set n equals to 100. Let's say I set alpha equal to 0.1. Then this says 90%. I wanted 90% coverage, and I got no more than 91% coverage. And that holds for any algorithm, any data set, any alpha, and any n. Okay, where n is the size of your calibration data set. Okay, there's a question in the chat, which is an important question. Doesn't this assume the training and calibration samples are representative of the true distribution? Yeah. So the assumption of conformal prediction is that the calibration data set and the new test point are exchangeable with one another. So in other words, they come in a random order. So one thing that implies exchangeability is IID-ness. So if they're IID, the calibration data set and the new test point, then this procedure will work. It does not assume that the training data set is representative of the new test point. So your model can be arbitrarily bad because the training data might not be representative. But as long as you calibrate properly, as long as you pick this Q hat and this Q hat is sort of representative of new data, then the procedure will work. So that is the main assumption of conformal. It assumes some sort of like quote unquote IID. Yeah. Oh, and also maybe now is a good time to address this other question, which is, does it assume that you have prior knowledge of the label? So there's ways of running conformal in unsupervised settings, but the sorts of guarantees that you get are slightly different than this. You can get sort of like type 1 outlier rejection guarantees with conformal in the unsupervised setting. And in the label noise setting, you can sometimes get guarantees with conformal, but it depends on the type of label noise. And yeah, so there's several references on this that I can send you. But people have studied sort of various permutations of this standard IID setting. Okay, so one thing to know about conformal prediction is that it goes far beyond classification. Okay, so we just talked about classification. The conformal prediction will work basically for any machine learning task. And the way that conformal works, just to abstract the sort of simple procedure that we just discussed, is first you have to have some sort of a heuristic notion of uncertainty. And this can be anything. In our case before, it was sort of like 1 minus the model's softmax score. That's sort of large when the model's uncertain and small when the model is certain. Okay, so that's the model's heuristic notion of uncertainty. Why is it heuristic? It's heuristic because we don't know that the model is any good. Okay, and then step one here of conformal is you define a score function. And the score function should be large when the model's uncertain and small when the model's certain. In our case from before, S of x comma y is equal to like 1 minus e sub I, which is 1 minus pi hat y I of xi. All right. So it's like the softmax score of the true class. And then you compute a quantile of those scores. All right. The scores evaluated on the calibration data points, I mean. And that's the Q hat that we had before. And if you look closely, the signs are kind of flipped here because E sub I is, before we took the quantile of E sub I, and now we're taking the quantile of 1 minus E sub I. So we're kind of targeting the 1 minus alpha quantile here instead of the alpha quantile. So sorry for this sign flip. It's just easier to explain this way usually. Now, if you look at this quantile, this is where the adjustment comes in. All right, so you should look at this and you should think 1 minus alpha, but then it's got this extra factor like n plus 1 over n. So as n goes to when n equals 100, this is basically like 101 over 100 times 1 minus alpha, roughly. Okay. So that's Q hat. And then at deployment, you sort of like look at all the possible labels, and then you check whether the score of your label will be less than or equal to Q hat. So you take all sufficiently like certain labels, right? So Q hat is like your certainty threshold, and S is your heuristic notion of uncertainty. You take all labels which are sufficiently certain. In other words, whose uncertainty score is sufficiently low. Right? And you make that a set, and then you have the guarantee that we had before. You have this, probability this thing contains Y, true Y. Okay, 1 minus alpha plus 1 over n plus 1. Sorry. Okay, so in the spirit of exploring the generality of this, let's also talk about the regression setting. So I'm going to explain conformalized quantile regression. Conformalized quantile regression is a strategy for doing this in regression, okay? So in the regression setting, we have a continuous Y, it's not discrete, and we've estimated the alpha over 2 and 1 minus alpha over 2 quantiles, all right? So this is a one-dimensional picture, and we'd expect if the model were perfect that the true Y would land within these intervals, but it's not going to because our quantiles are not necessarily any good, okay? So the idea of conformalized quantile regression is to like inflate or deflate these quantiles by a constant using our calibration data set in order to make sure that they actually have the coverage guarantee marginal. All right. So the way that this works is your E sub I, in other words, your uncertainty score here. I guess I should just call this S of X, Y. Will be the projection of the true label onto these quantiles. So that distance, that projective distance is going to be your uncertainty. All right. And now we have a bag of these, I equals 1 through n. And we're going to take this special quantile of them. We said roughly 90% quantile if alpha equals 0.1. Now we know exactly what the adjustment is. It's n plus 1 times 0.9 over n. Okay, so that's actually the thing we plug into there. And then we form prediction sets by inflating or deflating, depending on the sign of Q hat, the naive quantiles by this adjusted factor. And then the guarantee that we'll get is basically like, 90% of true labels landed, inside the intervals when they were inflated by Q hat. Okay. So it will give you coverage when you do that. And all conformal procedures are sort of very simple like this. They all have this flavor of step 1 is the hard part, define my score, and then step 2 and 3 are exactly the same. Okay. So that's it for the tutorial on conformal. Now I'm going to go into conformal risk control, which is a recent extension that my colleagues and I at Berkeley worked on. Maybe we can ask any questions before that we move into that.
There's one in the chat.
Yeah. So is it possible to prove that the confidence set denoted by C of X is small or as small as possible? So in a certain sense, conformal does give you the smallest set. And just pulling up this guarantee from before, what this guarantee is telling you is that the conformal prediction procedure is not like unfairly inflating the size of your set. So by that, I mean, the inflation of conformal is not larger than like 1 over n plus 1. Okay. So in other words, the penalty that you get for running the conformal procedure is not larger than 1 over n plus 1. So in a certain sense, that's telling you about the size of the set, because the coverage, the coverage only grows when the set grows. Now, I can't guarantee you that the set that you'll get will be the smallest one that satisfies marginal coverage, because that depends on the model. So if you give me a perfect model, actually, the procedure that we described here, if you run this procedure with a perfect model, it will provably give you the smallest set by sort of Neyman Pearson type argument. But if you don't assume anything about your model, you can't tell me that you've done that. But you can tell me that the conformal procedure hasn't unfairly told me that your model is no good. Does that make sense?
Hello.
Hi.
Can you hear me?
Yeah.
Yeah, I'm the person who asked you the question. Thanks a lot for your explanation. So what if I understood this theorem 1 correctly is basically holds for every model. So even for random model, it holds. But if you have optimized your model, then you can get a smaller size.
Yeah, exactly. Mm-hmm. And there's various notions of optimality that you might have.
I see.
Yeah.
Thanks a lot. Thank you. Thank you.
No worries. Thank you for asking. Okay. If the label structure is hierarchical, can the coverage guarantee not just that the true label is in the confidence set, but also all possible entities in the confidence set labeled that parent node only? Yeah, you can do that with conformal risk control. Actually, I have a hierarchical label example later. So why don't we go into this technique? Conformal risk control is very much geared towards these sort of more structured problems that are not simple one-dimensional like regression examples, where your notion of error might be more complicated, like the one that you're describing. So the thing to notice with conformal risk control is that coverage is a risk. Okay, so in particular, if you take this probability, the probability that my label is not in the set, conformal prediction will guarantee me that that's less than or equal to alpha, right? But now, remember that probability is the expected value of an indicator function. It's the expected value of indicator y is not in the set. And if you just look at this indicator function here, you can think about it as a loss. You can think about it as a loss where you incur a loss of 1 when I don't contain the true label and a loss of 0 when I do. Okay? So the idea of conformal risk control is, in these more structured problems, what if my notion of error is not 0, 1? What if different mistakes cost different amounts? What if I have a hierarchical structure and, I want to make sure that my graph distance to the true node is, so on and so forth? Or what if I have a complicated label where it's okay to miss a little bit of it, but I don't want to miss most of it, like, a segmentation mask or something like that? Well, then, 0, 1 doesn't make sense, because that's not the natural notion of error for that problem. Instead, it turns out that actually you can just run conformal prediction with something other than a 0, 1 loss, and it will ensure that that entire expectation is controlled. right? So you can basically replace this with any loss function that's monotone in the set size, essentially. And then you can certify that that's less than or equal to alpha. And then basically the same guarantees hold for any alpha n, any data set, any model. So as a running example, we talked about segmentation, but let me show this again. This is a tumor segmentation problem, okay? So your x's are tumors. This is your x. And then you have a model like that takes x, and then it turns it into like the probability that each pixel in an m by n image comes from a tumor. Okay, so for each pixel in the image, my model is going to give me probability it comes from a tumor, right? Estimated. And then, of course, my label y is going to be a binary mask, which is 1 when there's a tumor and 0 when there's not. Okay. Now, what we're going to do is we're going to do the most naive thing. We're going to take the output of the model and we're going to threshold it at some level such that I get a false negative rate guarantee. Okay. So in particular, here's what we're going to do. We're going to take the probability hat of a tumor, and we're going to threshold it like this. We're going to threshold it at some level lambda. Okay? So when lambda is 0.3, that means I get a small set. When I get lambda 0.7, that means I get a large set. What I'm doing is I'm thresholding at level 1 minus lambda. Okay? So when lambda grows, my set shrinks. When lambda shrinks, my set grows. I'm sorry, did I say that backwards? When lambda grows, my set grows. When lambda shrinks, my set shrinks. All right? And our goal is to select a set that has bounded false negative rate with the tumor. In other words, one that contains the majority of the tumor with high probability. Okay? So that's the false negative rate here. It's just the fraction of tumor pixels that I contain over, and let me replace that with a C. Sorry about that. The fraction of tumor pixels that I contain over the fraction of tumor pixels total. All right? Any questions about this like motivating problem?
So this is again like agnostic to the model. Like the model is bad, we simply are just like high risk.
Exactly. Exactly. We're going to try to certify that this thing's less than or equal to alpha, regardless of the model.
Got it.
Okay. So in the conformal risk control procedure, what we do is the following. We define the empirical risk, okay? So what does that mean? That means we took 1 over n, sum I equals 1 to n, of our loss function evaluated on our set with threshold lambda. And we just parameterize that function for all lambda. Okay, so in other words, I calculated like the false negative proportion for all of my calibration data points. And then I took the average. And I looked at that as a function of the threshold. Okay. Now, I can choose lambda hat to be the smallest lambda such that the empirical risk is less than or equal to this quantity, which is just slightly less than alpha. Okay, so if you were doing this like naively, like without any statistics at all, what you would do is you would find the smallest lambda such that this thing's less than or equal to alpha. You just take, your calibration data points and then make sure your threshold is like, you find the threshold such that the risk is below alpha. So here we're doing something just very slightly different. We're thresholding at a slightly more conservative level, which decays as 1 over n. All right. And then we pick that as our threshold value. And then we can just deploy that. So that will be the threshold at which we segment, we like output the segmentation masks. Lambda hat. All right. And then this will be our prediction set. All right. So the theorem that you get with this is quite similar to that of conformal. In fact, it almost reduces to that of the conformal guarantee. this right-hand side says that my expectation is controlled. Okay, so I give you what I promised. And then in addition, I promised you that I didn't unfairly inflate, just as we were talking about before. Okay, so the signs here are flipped from conformal. But imagine that this loss is the 0-1 loss. Okay, if it's the 0-1 loss, then this thing becomes coverage. Or it actually becomes 1 minus coverage. Then I say 1 minus coverage less than or equal to alpha, less than or equal to alpha minus 2 over n plus 1. And that's exactly the conformal guarantee. It is exactly the same guarantee, except that this is a 2 instead of a 1. Okay, so the like tightness bound is off by a small constant from the conformal one, and the upper bound is exactly the same. Now, in addition to that, what's really interesting is this algorithm reduces exactly to the conformal prediction algorithm when you use the binary loss. So in the 0-1 loss case, L hat is equal to Q hat from before. Lambda hat is equal to Q hat from before. Okay. So that's kind of fun. It's a direct generalization of conformal, in other words. Also, the prediction sets are the same as the ones that conformal gives you under the 0-1 loss. It's just that you can literally run the conformal algorithm with different loss functions, and everything works out basically exactly the same, except for this 2 instead of a 1. All right. Any questions on the procedure before we move on to like a worked examples?
Not really.
Okay. Yeah, so maybe I'll just say what we would do precisely in the tumor example. In the tumor example, what we do is we calculate the sigmoid scores of the model. So those are like the F hat from before. Let's just call those Z sub i's. And then we define a little function, like in Python, that says, get me my empirical risk. And the empirical risk is just going to be the average overlap between your tumor and your predicted set. Okay? So that's what the R hat is going to be. And then you set lambda hat as before and deploy. And when you deploy your segmentation mask, you're going to deploy, where the model is greater than or equal to the threshold, where the models like softmax sigmoid scores are greater than or equal to the threshold. All right, so you just, in other words, this is F hat of X. This is like a slice of tissue, right? And this is lambda hat. This becomes your prediction set C. Okay. So the first example actually is this hierarchical classification example. It's not exactly what was asked about before, but it's pretty close. And I'll go through it. So the thing to notice here is that the only thing you have to define is a loss function, okay? So this is an ImageNet. In ImageNet, we have like 1,000 labels, and we have this classifier that outputs estimated scores. And then I'm also going to give you a loss function. The loss function is going to operate on a graph, right? It's going to operate on a label tree. And in ImageNet, there is a pre-baked label tree called WordNet that you can just download and use. Okay. And the basic idea of the loss function is that, let's say I have a ground truth label, which is like, I don't know, Siamese cat or something. That's this Y. And then I have a prediction set, which is, an interior node of the tree. It's like Spaniel. Then what I can do is I can define a graph distance between the true label and my prediction set, which is basically like how many hops did I need to go up the graph until I intersected with some ancestor of my true label. See what I'm saying? So in this case, it's 2 because, it's not a spaniel, it's not a dog, but it is an animal. So I needed to go 1, 2 jumps. Okay. And then what you can do is you can define a sequence of like sets that threshold, like this C sub lambda thing, and I've written it again as T down here, but it should be C. This C sub lambda thing is just like, you index it by the amount of mass that the set contains. So you look at all the labels of the interior node, and you say, stop growing my set when I reach 0.7, and you start at like the maximum likelihood estimate of the label. So you just keep going up the graph until you hit 0.7 mass in the children. And what you can do is you can like you can set this like probability threshold such that you achieve whatever graph loss that you want. All right, so that's what we've shown on the left. On the left, you know, the black is the ground truth label. The blue is the prediction set, which in this case is actually just an interior node of the tree. And then the red is the model's like top label. So the incorrect label that the model output. So for example, the model thought this was a candle. The ground truth label was spotlight, which is also wrong actually. But our procedure output lamp, right? Our conformal risk control procedure, which is great because this is a lava lamp. And, you know, you can do the same thing here. Model thought it was a candle. It's really a table lamp. We output lamp. Great. You know, these are more examples. Okay, so we just went up the tree slightly in order to get the true parent. Okay, now you can take this further. I'll just show a couple examples briefly. We can just take the loss function and be the false negative rate and do something with a generative model as well. So let's say I have a disentangled latent space. I can predict intervals in that latent space that give me uncertainty on those latent factors. So, you know, that now I can give you, if I have a disentangled space, I can give you a model that's not sure about whether someone's smiling or not sure about their hairline or their gender or so on. And then I can propagate those intervals back through the generator to get you sort of like meaningful intervals. Okay, so what does this look like? This looks like, you know, these are, by the way, intervals with rigorous probabilistic guarantees and also sort of meaningful visual representations that are semantic in nature rather than numerical, you know. So let me just give you an example of this. So here, the input, let's say I give you an input that's perfect, right? So I've not masked it at all. I'm doing in-painting. Now, what I can do is I can propagate that, try to give you uncertainty on it, and visualize the uncertainty as propagated to the generator. And then these are like the lower and upper quantiles of my uncertainty, okay? And as you can see, there's none because the images are sort of the same. But now let's see what happens when I block out the eyes. When I block out the eyes, what happens? This is the ground truth, remember? And now look at the intervals. In one, there's glasses, and then there's one, there's no glasses. So the model's not sure if there are glasses because the glasses have been masked out. Okay, that's pretty cool. And now here we've blocked out the mouth. And the uncertainty says, I'm not sure how much this person is smiling because I haven't seen the mouth. Okay, but it knows that they are smiling a little bit because you can see the sort of laugh lines. And then, of course, if you block out everything, you get trash. Wide. This is a wide interval, right? We're also working to try and like help doctors in the clinic deploy these rigorous uncertainties. So a lot of times doctors want to like automate some part of their workflow using some sort of AI algorithm. So in this setting, what happens is that doctors are trying to do spinal stenosis grading. So this is a healthy spine right here. That's like your spinal cord, and these are your vertebrae. And then this is stenosis. This is a spine with stenosis. Stenosis causes back pain. It's a pinching of the nerves. Right? And what they're trying to do is, it's kind of like onerous for doctors to go through and like grade the severity of the stenosis, because there's a lot of places where stenosis could be. It could be here, here, here. Where's my red? Here, 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 here. But also you need to kind of look at the spine from 3 different angles in order to see whether, you know, there's like left foraminal spinal stenosis, and then there's, you know, the left, right, and center sides of the spine, basically. And then also all the disc levels. So it's kind of a pain. So they want a model to like pre-label things so that they can go in and not have to type so much during their exams. Okay. So in other words, they're trying to fill out this table where the rows are the disc level. The columns are left, right, center, as we said before. And then the entries just are severity from 0 to 4, meaning like, or 0 to 3, which is like no stenosis, mild, moderate, severe. all right? And what we can give them with this risk control framework is sets that are guaranteed to contain a high fraction of the true severities, or sets that, like, you know, aren't too far off from the true answer. In other words, you gain a higher penalty if your set doesn't contain 4 and it only contains 0. And so that's what we're working on. This is with some collaborators, in particular Charlie Liu and Stuart Pomerantz at Massachusetts General Hospital. You also get some pretty interesting things when you look at this data. So this will be the last thing that I say. But when you look at this data and you just like rank the scans from like most to least uncertain, you get all sorts of crap in the uncertain cases. Like, this is a tumor, it's a schwannoma, which is a tumor of the Schwann cells. These are metal artifacts. So somebody had like metal in their body, and then when they took the MRI, it caused an artifact. Because of course the MRI uses, like, you know, magnetic spin in order to construct the image. And then these are motion artifacts. So somebody was moving around. So the algorithm's uncertain, it outputs a high uncertainty. Which is useful because then we can use that to run like selective classification procedures that like only give you an answer when the model is certain. The most uncertain person in this data set was an achondroplastic dwarf. So the spine was very malformed, and definitely the model should not be outputting answers there. Okay, so I've gone through all my examples. Maybe we can stop and talk. I know we've already had some questions, but maybe we can answer what remains.
Like in this setting, like of detecting the stenosis, the basic assumption is like, I understand like the conformal prediction sets, like they are agnostic to the quality of the model, but to really uncover these outliers, the model has to be somewhat good. Like, or like,
yeah, absolutely.
Precise question is like, if the model is like just half as accurate in the prediction, would I still uncover, like I get the guarantees, but would I still uncover the outliers?
No. Okay. I mean, you can guarantee to uncover the outliers using conformal prediction, but the problem is if your model is like random and you want to like discover some fraction of outliers or something, then you're going to need to output like a huge amount of data. Right, so you can like, I can always give you the outliers by outputting the whole data set, for example.
True.
Oh, by the way, I'll mention this before we stop talking, but there's a differentially private version of conformal prediction if you guys are interested in it. So the way that you do that is basically like you use a private quantile algorithm, and then you can show that all the conformal guarantees propagate through because the quantile that you get is more conservative.
I see. But the underlying model, there are no like DP constraints.
So you don't get DP on the underlying model. What you get is DP on the calibration data set, which was used to calculate the quantile.
Pretty useful stuff. Like the underlying model can be simply a DP trained one plugged in.
Exactly. Exactly. So the relevant paper for that is private prediction sets. That's what it's called.
Thanks. There's one in the chat also.
Oh, question in the chat. Is the goal of conformal prediction to make models well calibrated? It is kind of. So oftentimes when we talk about calibration, what people mean when they say calibration is this thing. Like stuff like this. And conformal prediction, so first of all, it's worth noting that this is kind of hard to get. Like calibration is a much more statistically difficult procedure than conformal prediction. Because in calibration, you're conditional on all of these, like all possible values of P, the probability. But in conformal prediction, you're just marginal over everything. So you're really only trying to estimate one quantile. So there are some technical differences in the sense that basically calibration wants your top probability to be correct. But conformal prediction does not give you that your top probability is correct. It just gives you a guarantee on the output set. And the distinction is important because giving you a guarantee about the set is much easier than giving you a guarantee about the calibration. Also, by the way, calibration does not imply conformal prediction will work, at least this form. You have to ensure that like all of the softmax scores of the model are jointly calibrated in order to get conformal to work. And that's even harder. That's even harder because you need to like bin every like rank, not just the most likely class, but second and third and fourth and so on. Does that answer your question? I have a teacher which is well calibrated. Instead of point label predictions, just possibly. So who worked on this? Let me send a couple papers to the chat. So there's some people who have worked on sort of like soft feedback with conformal. So one group to look at is this. There's this group at MIT, Adam Fish and Tal Schuster. Look up that. Who do work on cascades with conformal. So they'll try to like make models more efficient. And there's some like notion of soft label that happens there that they call expanded admission. So I'll put that here. And then I think John Ducci's group, if I recall correctly, does work like this. Let me find this paper. Predictive inference with weak supervision. That's right. Maxime, Suyash, Alner, and John. Yeah, I think that this is the correct paper. So you might look at these two. They're sort of along the same lines, but I'm not sure that anyone has done exactly what you're saying. There are also people who have done this, sort of like followed this type of idea with human, like students, if you will. So let me find that paper. That's from Max Planck. Yeah, I might have to send this later. I don't remember exactly what it is. Yeah, okay. I'll have to send this one later. I don't remember exactly where this paper comes from. Man, it's on the tip of my tongue. Maybe we can move on to some other questions and I'll just think about it in the background or look it up.
I wanted to ask something like, this is like more on a very high level.
Mm-hmm.
So to sort of like summarize it, what it seems like conformal prediction, like for example, we are making progress on, say, in most of the discriminative settings that you talked about.
Yeah.
And it feels like conformal prediction, it gives you extra benefits on top of the model where you have already invested in making them like work really well.
Yeah.
It seems like really complementary. Like one must do it. Like you don't lose anything.
Yeah, you basically lose nothing.
Yeah, and you get these very excellent guarantees on top. Like in practice, like for example, in the paper, you do have some examples. Like when you actually deploy it, or when you actually do try it in practice, are there like caveats you run into where like say, I'm not sure, like some data sets, like the models you see, the data sets being like really fine grained. For example, the squirrel example you talked about.
I would say that like the thing about it is that conformal prediction is usually just an excuse to get practitioners to incorporate some form of uncertainty in their problems. So I would say that like what's always better than doing nothing is like having some uncertainty. That's like, it's never bad to have more information, right?
Mm-hmm.
So a lot of the like sort of job of the day-to-day like conformal salesman is not so much even about conformal. It's more like just convince people that uncertainty is a valuable like thing, because a lot of times, you know, practitioners don't do that. I mean, it's easier in the medical setting. In the medical setting, they know it's important. It's like, of course we need it. In the self-driving setting, of course we need it. But you talk to people that are doing computer vision, right? Like one of my advisors in the computer vision group, and I have a lot of friends that do vision, they don't really output uncertainties. And that's because they're not deploying models, right? So it's like, why would I need uncertainty when I'm just trying to make something work? And that's okay, but maybe that's not the right audience for a method like this. The right audience is people who are deploying, people who want to create robust deployments, which might be different than people like developing vision algorithms in order to like prove out a new concept. So that's one caveat, and then conformal, as you said, it's like once you've convinced somebody to do uncertainty, conformal is just like, just do it. Why not? I mean, it's just like, if you have, the only thing is you need a calibration data set, right?
Yeah. So it's pretty much drag and drop. Like if you have, okay.
Absolutely. Yeah, absolutely. Then there's the other issue, which is conditional like performance, as we talked about before. It's so conformal, everything is on average. So it's like, this won't, like, I won't give you coverage in every class. I won't give you coverage on any particular image. I won't give you any of that, any region of space. It's just all average. Having said that, there's a lot of work in conformal prediction trying to like make procedures with good conditional performance, even though the conformal algorithm doesn't assure you that you have conditional performance. So, yeah. So these are like the practical things. Calibration and test set are exchangeable as hard for deployment, for sure. But as you know, as I was talking about before, that like, so first of all, there are ways of like adapting conformal to various shifts. For example, covariate shift. You can use sort of like, you can decay out old scores, and there's a bound that will tell you that my coverage won't be too bad as long as the distribution is shifting slowly. Stuff like this. So there's a lot of work done on like taking conformal past the standard IID setting. Having said that, this is still a problem, right? I mean, you need to observe repeated observations in order to do any statistics at all. There's just, statistics is about repetition. So there's nothing, you can't really get away from that. But it's still often better than nothing. Like, people actually literally will do nothing sometimes, often. And this is, conformal is often like an excuse to just talk to people about why they need uncertainty, which is, and basically act as an ambassador for statistics itself. That doesn't mean that conformal is the unique way to do that, but I'm just telling you about my like observation, like when working with practitioners, that it's like, yeah, I can actually help you quantify your uncertainty, and under certain assumptions, I can give you a guarantee. So.
If there is, yeah, if there's no other question, I guess this is a good time to thank our speaker.
Thanks so much for having me.
Yeah. Thanks a lot. This
Thanks
was
for all the
very,
great questions too.
yeah, very, very engaging. Yeah. So yeah, thanks everyone, and see you everyone next week.
Thanks so much.